Okay, so we want to pick up where we left off. We were talking previously about falling objects, but we were ignoring the effects of air resistance. If something is falling through the air and air resistance is acting on it, then its acceleration is going to be reduced. It's going to have a lower acceleration. And the bigger the effect of air resistance, the more reduction in acceleration that you get. So let's consider a situation where you have a guy in a parachute, and I'm going to pick the green guy to start with. There's two forces acting on him. So there's his weight, so he jumps out of the airplane, and his weight immediately makes him start falling towards the earth. The gravity is pulling down on him. That's what weight is. Weight is the force of gravity. And so gravity is pulling him down to the earth, but he opens a parachute, and the parachute has a really big surface area. And so it catches a lot of air as he falls. And that air, as it passes through the parachute, it slows him down. And of course, that's what parachutes do. They slow you down so that when you land on the ground, you're not moving so fast that you injure yourself. But we want to see what the impact of this air resistance is on the motion of something falling through the air. And so we're going to be thinking about that for a bit. Now, what's going to happen if you have an object that's falling, and so some object is falling, and it's going to be speeding up and speeding up. Now, if you've ever stuck your hand outside of a window of a moving car, you felt the air resistance pushing back on your hand. And you know that as the car goes faster and faster, you feel more force of air resistance. And so this is what's going to happen to the falling object, because as it accelerates, it's going to be moving faster and faster, and so the air resistance is going to get bigger and bigger. And so the acceleration is now no longer constant, it's constantly changing. But we're going to see what the effects of this are with some basic ideas. So let's ask a question. If a 20 Newton falling object encounters 5 newtons of air resistance, and remember, Newton is like the unit of force in the metric system, so it's not the same as a pound, but it's the same kind of thing as a pound. It's a type of force. In fact, each Newton is about a quarter of a pound. Not quite, but almost a quarter of a pound. So anyway, we have our question here. If you have a 20 Newton falling object that encounters 5 newtons of air resistance, what's its acceleration and fall is A, less than g, B, more than g, C, equal to g, or D, terminated. It doesn't accelerate at all, or it accelerates for a while and it stops. Well, the answer to that is that it's going to be less than g, because the air resistance is acting against it. So think of it this way. If an object were falling and there were no air resistance at all, the force of gravity would cause that object to accelerate at little g. But because there's air resistance acting in the opposite direction, in this case you've got 20 newtons pulling it down and 5 newtons pulling it up with the air resistance, then you have a net force of 15 newtons, not 20 newtons, and so the acceleration is going to be less. Now in this slide, we're going to talk about an application of Newton's second law, and it's called terminal velocity. And the terminal velocity is what happens when something falls through air resistance. Now, the idea is this. So you drop something through the air, you drop something off of an airplane, it's falling down towards the ground. As it falls, it goes faster and faster, it gains speed. And so the force exerted against that object by the air resistance increases as well. So the amount of acceleration gets reduced. And so eventually the force of air resistance will continue to increase until it equals the weight of the object that's falling. In other words, the object is falling faster and faster, so the air resistance gets higher and higher. So I've got this object here, it's falling down, it's going faster and faster, the air resistance is getting stronger and stronger. If it keeps falling faster and faster enough, eventually it'll be going so fast that the force of air resistance is equivalent to the force of the weight. And at that point, there's no net force acting on the object, so it will stop accelerating. That doesn't mean it'll stop moving, it means it will stop increasing how fast it's going. And that point where the velocity has reached a constant value, it's no longer increasing, that's called the terminal velocity. And so we can say that the terminal velocity, that's the speed of the object when, so it's falling faster and faster. Eventually it reaches this speed at which the air resistance equals the weight. And at that point, it stops accelerating. It keeps that speed for the rest of the time that it's falling. And if you're curious, the terminal velocity of a human being is about 118 miles per hour. So if you jump out of an airplane and you don't have a parachute, that's about how fast your body will be going when you hit the ground. About 118 to 120 miles an hour, which is pretty darn fast. So imagine a car moving 118 miles an hour plowing into you. It's like basically the same idea, except you're the one that's moving and you hit the solid ground. So people that fall out of airplanes sometimes do survive. They might fall in, a haystack or something that slows them down. But usually, if you're thrown out of a plane or you jump out of a plane without a parachute, you are going to have a bad day when that happens. So let's test our comprehension of this with a simple question. If a 50 Newton person is to fall at terminal speed, the air resistance needed is A, less than 50, B, 50, or C, more than 50, or D, none of the above. Okay, so in order for the person to be at terminal speed, the force of air resistance has to be the same as the force of the person's weight. And so if this person weighs 50 newtons, that has to be the force involved. And so the answer is that 50 newtons is what the air resistance needs to be to make a 50 Newton person be at their terminal velocity. Okay, here is another example question. As a skydiver falls faster and faster through the air resistance A increases, B decreases, or C remains the same. Well, we know that the answer is that it's going to increase. As you go faster and faster, the air resistance increases. Now, once you reach that terminal velocity, you're no longer going faster and faster. The air resistance keeps the same amount. But as you're going faster and faster through the air resistance is going to get bigger and bigger. All right, here's a trickier question. As a skydiver continues to fall faster and faster through the air, the net force A increases, B decreases, C remains the same, or D, there's not enough information. So let's think about this. The person is falling, and so there's the person's weight, or the force of gravity, is pulling them down. And then, before they start moving, that's the only force acting on them. But once they start moving, there's going to be a force of air resistance which is in the opposite direction. And that air resistance is going to get bigger and bigger and bigger. So what's the net force? As the air resistance gets bigger and bigger, the net force is going to get smaller and smaller. You start out with just gravity. Then you get a little bit of air resistance, which makes the net force smaller. Then you get more air resistance as you go faster, and that makes it smaller and smaller until eventually the forces cancel out completely. And so the answer to this question is the net force decreases. What about her acceleration? So this question says, as a skydiver continues to fall faster and faster through the air, her acceleration does what? And we know from Newton's second law that F equals ma, and mass is a constant here. She's not like, she doesn't have a backpack filled with sand and the sand's leaking out. The amount of mass that she has is the same. So the acceleration and the force track together. In other words, we just said that the net force was decreasing. So if the force is going down, that means the acceleration has to go down too. And so the answer for that, it also decreases. Now let's think about another situation. Consider a heavy and a light person with the same size parachutes jumping together from the same altitude. So they leap from the same height at the same time. And the question is, And we could even say they open their parachutes at the same time. So the parachute opens the minute they leave the plane. And what happens to them? Which one is going to hit the ground first? So here are the options. You can say that the lighter person is going to hit the ground first, the heavy person is going to hit the ground first, both are going to hit the ground at the same time, or there's not enough information. Now, based on what we've said, you might be inclined to think that they're going to hit the ground at the same time, because we've said that falling objects always hit the ground at the same time. Except we said that was true when you can ignore air resistance. But this is a type of a problem where air resistance is very important. You cannot ignore it. So actually, the heavier person will hit the ground first if air resistance is effective. Why is that? Because, so let's say this person weighs, 100 pounds. So this person here weighs 100 pounds. And let's say this person weighs 200 pounds. So this one weighs 100. And this one weighs 200. What's that tell you? Well, this person is going to reach the terminal velocity when the air resistance is 100 pounds. So when the air resistance matches his weight, he's going to stop going any faster. But this guy, when they're both going 100, when they're both going at the speed to give 100 pounds of air resistance, this guy's got 200 pounds and only 100 pounds of air resistance, and so he's going to continue to be going faster and faster. So when this guy over here stops going faster, this guy's got quite a ways where he's going to continue going faster, and so he's going to get ahead of the guy with the blue parachute. So the green guy, or the heavier guy, is actually going to hit the ground first. So we've covered Newton's first and second laws pretty extensively now. We're going to move on and cover Newton's third law, which is the last of Newton's three laws. But in order to do that, we're going to talk about a couple of basic definitions. The first is the definition of a force, which we can say is simply a push or a pull. That is all that a force is. It's simply you're pushing or you're pulling on something, you're being pushed, you're being pulled. And when you apply a force to something, that means there has to be some interaction. So an interaction occurs between one thing and another. So here's an example. When you push against a wall, you're interacting with the wall. And it turns out, we're going to see, the wall pushes back. So here we can define Newton's third law of motion, which is sometimes called the law of action and reaction. Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. So here's an example. When your hand presses against the wall simultaneously presses against your hand. The hand and wall press on each other with equal and opposite forces. Here's another example. I weigh about 160 pounds. When I'm standing on the floor, I don't go crashing through the floor because the floor is pushing back against me with an equal and opposite weight. And so my 160 pounds being pulled down by gravity is matched by the floor pushing me up at the same weight. And so for every force, whether you're pushing, whether gravity is pulling, anytime you have one thing acting on another thing with a force, there is an equal and opposite force involved. So let's check this out. Here's another example. A soccer player kicks a ball with a 1,500 Newton amount of force. So he applies 1,500 Newtons of force to the ball. The ball exerts a reaction force against the player's foot of how much? Less than, equal to, more than 1,500, or none of the above. And of course, I think you probably guessed the right answer, 1,500 Newtons, because it has to be equal. That's what Newton's third law says, equal and opposite. Now, we can talk about the two forces, but we want to be able to distinguish between them. And so we call one of them the action and the other the reaction. So if I push against the wall pushes back. Me pushing against the wall is the action. The wall pushing back is the reaction. So that's the basic idea. And so if we look at this, we can see, for example, a car being pushed along the road. Now, what's happening is the tires are being rotated, spun around by the motor of the car, and as it does, it pushes off against the road. So the tire pushes on the road, and the reaction is that the road pushes against the tire. And so that propels the card forward. Here's another idea, a rocket expending gas out the back. So you've got the rockets burning fuel and the exhaust comes out the back. So the rocket pushes against the gas and the gas pushes on the rocket. So the rocket pushes the gas out, but the gas pushes back against the rocket with an equal and opposite force, and that's what makes the rocket go forward. Here's another example. A man pulls on a spring, that's the action. The reaction is that the spring pulls back against the man. Here, gravity is another example. Here you see someone dropping a ball off the Leaning Tower of Pisa, which is a famous building in Italy. And so gravity's pulling on the ball once he lets it go. That's the action, the earth pulling on the ball. And the reaction is the ball pulling on the earth. How about that? So, hopefully all those make sense. Now, this example is a little bit silly, but it's worth thinking about maybe. So the idea is this: when you step off a curve, gravity is going to pull you down. So you fall down off the curve because gravity is pulling you. According to Newton's third law, what's the reaction force to that? Well, you actually pull the earth up towards you a little bit. Isn't that weird? You pull the earth upward. That's the answer according to Newton's third law. But how is that possible? How is it that you are actually pulling the earth upward? Well, remember, Newton's second law tells us that A is equal to F over m. So when you step off the curb, you get a certain acceleration because the force of gravity is divided by your mass. Now the earth feels the same amount of force, but its mass is so much bigger, the acceleration is so small that you can't hardly even see it. In fact, you can't see it. It's that small. So we know that this is true, but it is a little silly to think about because it's such a small effect that we would never ever really have to worry about us moving the earth. But conceptually, hopefully you understand that, in fact, that does have to happen. And it's worth thinking about the effect of Newton's third law of motion on different sized masses. And so remember that the acceleration that a body undergoes is equal to its force divided by its mass. That's Newton's second law. So what happens if you have different masses? Well, if the mass gets bigger, you're dividing by a bigger number, so the acceleration gets smaller. That's the effect. And so a bigger mass means a smaller acceleration. A smaller mass means a bigger acceleration. So let's think about firing a cannon. So basically, when you fire a cannon, there's a chemical explosion from the exploding gunpowder, and gases expand, and they push the cannonball forward, and they push the cannon backwards, and so the cannon recoils. If you've ever shot a rifle, you feel the same thing. You brace the rifle against your shoulder, you pull the trigger, you feel the recoil. That's because of Newton's third law. Newton's third law says that basically the forces have to be equal and opposite. So the effect is that the gun is getting the bullet pushed forward and the gun gets pushed backwards. Now, when that happens, the accelerations of the cannonball and the gun are dramatically different. The cannonball goes much, much faster than the cannon recoils. Why is that? It's because of Newton's second law. A equals F over m. What does that mean? Well, the mass of the cannonball is small, relatively speaking, so you get a big acceleration. And so the cannonball accelerates down the barrel of the cannon, and it's going really fast by the time it leaves. Whereas the cannon itself has a much bigger mass than just the cannonball, and so its acceleration is smaller. It's still big enough to make the cannon kick back, but it's not going to be going nearly as fast as the cannonball itself. If it were, that would make cannons not very useful things, right? But the fact that the cannon has a much bigger mass means that it won't recoil as much, and the cannonball can be propelled forward with a very high velocity. Let's look at another example. We've got a high-speed bus colliding head-on with an innocent little bug. The force of impact splatters this poor little unfortunate bug all over the window, or the windshield of the bus. So what do you think is greater, the force on the bug or the force on the bus? So your options are the bug gets hit harder, the bus gets hit harder, they both get hit with the same force, or it's impossible to say. Well, what's Newton's third law tell us? For every force, there is an equal or same amount of reaction force. So a lot of people, if they were asked this question and they'd never studied any physics, they would be inclined to say that the bug gets the most force because it gets splattered. But actually the forces have to be the same. Now the effect of those forces is different. Why? Because A equals F over M. And the bug is very, very tiny. So it experiences a massive acceleration, whereas enough acceleration to smush it. Whereas the bus has got a much bigger mass, and so it's dividing by a much larger number, and its acceleration is low. So that's why the impact seems to be different. The force is the same, but because the masses are different, you get different accelerations. Here's another question. Now keep in mind, these are Newton's third law questions, so that's a big hint. If two people of equal mass on a slippery ice push off from one another, will both move away at the same speed, but in opposite directions? The answer is yes. So options are yes, but only if they push equally? No. They can't not push equally, because for every force there's an equal and opposite reaction force. So whatever they're pushing with, there's going to be an equal and opposite force acting on the other person. So the answer is yes. Now, when you're talking about Newton's third law, it's very important for you to define what your system is. So let's consider here an orange, which is enclosed, and there is a simple applied force that is causing the orange to accelerate along the rules of Newton's second law. So I've got a force here, and that force is going to pull the orange, and the orange is going to accelerate that way. And so Newton's law tells us that the acceleration is equal to the force divided by the mass, and everything makes sense, hopefully. And what we have noted here is that we have not shown any reaction pair forces. There's no action-reaction here. There's just the action. That's because we defined our system to include just the action force. Now here is a different situation. We have the orange is accelerating forward because there's an apple pulling it. And so that's what's actually creating that action force. That action force is being created by the apple. Now, the action force is created by the apple. There will be a reaction force acting on the apple created by the orange. Now, the question is, how could you possibly accelerate this orange if there are equal and opposite forces? There's an action and a reaction. So why don't those forces cancel and make it impossible to accelerate the orange? It's because these forces act on different things. And so if you want to know what's happening to the orange, you have to look at only the forces acting on the orange. This reaction force here acts on the apple. It doesn't act on the orange. So it doesn't count for that. And so these action reactions only cancel if you are including the entire picture. And here, we're only looking at what's happening on the orange, so the forces don't cancel. But if instead we consider both the apple and the orange together as being our system, so that means that these forces are acting on the system both. And so if only the orange were our system, then only this force would be acting on it. But since we are talking about this whole thing being our system, both these forces, equal and opposite forces, that force to the right and that force to the left, equal and opposite forces, they are going to cancel. And so there's not going to be any acceleration caused by these two forces because they're an action-reaction pair within the whole system, and they cancel. And so that means that this system as a whole will not accelerate. But in the real world, that's not the entire picture, because the real world has friction, air resistance, that sort of thing. So let's look at this picture when we have the action of friction on these things as well. And so we're going to have the same internal action and reaction forces between the orange and the apple, and they're going to cancel each other out. But there's going to be a second pair of action-reaction forces between the apple's feet and the floor, and we want to look at what the effect of that is going to be. So here we have the original two pairs, the action and reaction pair that we had before. So we have that force and that force. But now there is a new force down here, and that's the force acting on the system, which is friction. And so one of these is acting on the system and the other is acting by the system. So in other words, the apple is pushing off on the floor, but the floor is pushing off on the apple. And that frictional force of the floor pushing off on the apple, that's what enables the entire system to accelerate. So yes, these internal forces now cancel each other out. But that doesn't mean that nothing can move. That just means that there have to be other forces at play to create that motion. Now, here's a slide, and this slide was provided by the publisher of your textbook. There's actually an error in thought here. So the question is, when the lift equals the weight of a helicopter. So we have a helicopter, the helicopter is flying, and so the helicopter has a weight, and it also has a force of lift, which is provided by the spinning rotors. And so the force of lift is pushing it upward, and the weight is pulling it downward. And the question says, when the lift equals the weight of the helicopter A climbs down, B climbs up, or C hovers in midair, or D, none of the above. And it turns out none of these is the right answer. That's a little bit of a conceptual boo-boo by your textbook. Now, the answer they wanted you to give was that the object hovers in midair. And that certainly can happen. If the object is hovering and the lift equals the weight, then those forces are balanced and it's going to hover. I actually thought about deleting this slide, but it made me think, when I thought about it, it made me think about something that might be useful to point out. The balancing of forces doesn't mean things don't move. It means their motion doesn't change. So if the helicopter were already going up and it increased the rotor speed or decreased the rotor speed so that the weight matched the lift, it would continue going up because the force is not making it slow down or speed up. It would just keep whatever speed it had. If the helicopter were going down and it increased the lift, instead of increasing going down, it would just go down at a steady rate. And so the rate at which the helicopter is moving can be whatever it is, up, down, or not moving, but it requires an unbalanced force to change that motion. So if the lift is greater than the weight, the helicopter will not only move upwards, but it will accelerate upwards. If the weight is greater than the lift, then the helicopter will not only move downwards, it will accelerate downwards. But if the lift equals the weight, the helicopter will maintain whatever kind of motion it has, because that means the forces are balanced. And so actually, that's not the right answer. It could be the right answer, but it doesn't have to be. So think about that because it's a very important detail. Okay, here's a tricky little question. How is a bird able to fly? What's the mechanism by which a bird flies? A bird flies by flapping its wings, pushing air down so that the air pushes it upwards, hovering in midair, or inhaling and exhaling air. Well, I think you probably recognize that's not a good answer. It's not going to be it's not going to be breathing. Hovering in midair, what does that even mean? It's not really relevant. I don't think it's going to be that. So we're left with a bird flies by flapping its wings or pushing air down so that the air pushes it upward. What's the right answer? Again, your book would tell you that it's this one, but I would argue maybe both, because the flapping of the wings is what pushes the air down. And so here's your bird, and the bird has its wings on each side, and the wings are flapping. And so as the wing flaps, it pushes the air down. So the air gets pushed down. Well, what does the air do? The air pushes back with an equal and opposite force. And that provides the lift that enables the bird to fly. And so that's the basic idea behind what enables a bird to fly. And that brings us to the end of the chapter.